factoring a polynomial, we're going to first start by defining what a greatest common factor is, or commonly known as GCF. So a greatest common factor of two or more numbers is the largest number that can divide into all the other numbers. So one method for finding the GCF, the greatest common factor, is called the ladder method. We use the ladder method for finding the least common multiple. Well, the ladder method can also be used to find the greatest common factor. So how it works is for the greatest common factor, you want to write the two numbers on one line. So we're going to do an example here. We're going to find the greatest common factor for 24 and 36. The next thing you want to do is draw an L shape around the numbers. So we're going to take 24 and 36 and we're going to find the greatest common factor. We're going to write the numbers in a line and we're going to put a little box around it. The next step is to divide out common prime numbers. Starting with the small, not necessarily have to start with the small, but I like doing it with the small and working my way down. Now remember what prime numbers are. Prime numbers are numbers that are only divisible by 1 and itself. So prime numbers are 2, 3, 5, 7, 11, and so forth. So these are prime factors or prime numbers. When you look at 24 and 36, the lowest prime number that's going to divide into both will be 2 because they're even numbers and 2 divides into all even numbers. You're going to take that 2, you're going to write it on the outside of the box, and then what you're going to do is divide that 2 into 24, and whatever's left is going to go underneath the 24, so you end up with 12, and then you're going to divide the 2 into 36, and whatever's left goes underneath the 36, and in this case is 18. And you want to continue this process until they no longer have common factors. And because I have 12 and 18, and they're both even, so I know 2 is going to go into it. So I'm going to take 2, I'm going to write it on the outside, and then I'm going to divide it into 12 and 18. When I divide 2 into 12, I get 6. 2 into 18, I get 9. And I see that with 6 and 9, I have a common prime factor of 3. So I'm going to write 3 on the outside, and then I'm going to divide it into 6, and I'm going to end up with 2, and I divide it into 9, and I'm going to end up with 3. Now at the bottom you see here 2 and 3, they no longer have any common factors. So now I can find the greatest common factor by simply multiplying the numbers on the left side. So you're going to multiply the numbers on the left side. In this case, I'm going to have 2 times 2 times 3 will equal 12. So 12 would be the greatest common factor for 24 and 36. Remember, the greatest common factor has to divide in evenly into every number that you're finding the greatest common factor for. 12 divides into 24, 12 divides into 36, and they have no more common factors. So that's why 12 would be the greatest common factor. Pause and try. In this case, I'm starting with 5 because both numbers end in 5. 5's a prime number, so I know that 5 is going to divide into 45 and 75. So when I use 5, I divide it into 45, I get 9. Divide it into 75, I get 15. Now it's smaller numbers, and I can see a common factor. The prime factor of 3 will go into here. So 3 will go into 9 3 times. 3 will go into 15 5 times, and then I have no more common factors. So my greatest common factor is going to be the numbers multiplied on the left side together. So 5 times 3 is going to give me 15. So 15 is the greatest common factor for 45 and 75. When we are looking for a greatest common factor and we have variables with exponents, what I want you to remember about variables and exponents is that when I have an exponent, what it means is that base is being multiplied to itself that many times. So x to the third is x times x times x. And x to the fifth is x times x times x times x times x. So this is what it looks like if I would break it into factors. Now keep in mind the greatest common factor has to divide in evenly into both. So you notice here that my greatest common factor is going to be that x times x times x, because it divides into x third, and it also divides into x to the fifth. So when we have variables and exponents, the greatest common factor will always be the variable with the lowest exponent. So the greatest common factor for variables and exponents is simply the one with the lowest exponent, and in this case would be x to the third. Pause and try. See here, the lowest exponent is the square, so the greatest common factor would be z to the second power. When we have a combination of numbers and variables with exponents, to find the greatest common factor, think of it by piece. You want to first find the numerical greatest common factor. So in this case, you could use the ladder method, or if you know off the bat that your greatest common factor will simply be 5, because 5 divides into each one of these numbers, and after you divide 5 out, there's no more common factors. We have a greatest common factor of 5. And then you want to look at the variable part, and remember that the variable part is simply the lowest exponent. So in the greatest common factor here, we would end up with x to the fourth. So finally, you're going to need to put it together when we're looking for the greatest common factor and we have coefficients and variables with exponent. So the greatest common factor for 10x to the fifth, 15x to the ninth, 25x to the fourth is going to be 5x to the fourth. Pause and try. Just looking for the greatest common factor here, and notice here that when I look at the numerical part, 6 divides into 12 and 24, therefore 6 will be the numerical part, and then the variable part will be the variable with the lowest exponent, so we have m squared. Greatest common factor here will be 6m squared. One key note, always check to see if the smallest number will divide into all the other numbers when you're looking for the greatest common factor. If the smallest of all the numbers divides into every other number, then that will be your greatest common factor for the numerical part. When we're talking about factoring out the greatest common factor of a polynomial, here's the step process that you want to take. Well, the first thing you're going to need to do is identify what the GCF is of the polynomial, which we just practiced in the previous examples. Then the next thing you're going to do is pull it out. And when you pull it out, you want to put it next to an open parentheses. So whatever that greatest common factor is, you're going to write, and then you're going to start it by having an open parentheses, and then what you're going to do with the greatest common factor is you're going to divide it from every term of the polynomial and place whatever is left inside the parentheses, and make sure you separate each term by the appropriate sign, whether it's plus or minus. So this is the steps to take, and I'm going to show you an example of what it would look like. So you want to factor out the greatest common factor, or the GCF, from 18x to the third plus 60x. So I need to factor it. I'm not just finding the GCF. I need to factor this polynomial so that I have the GCF and the parentheses of whatever is left over. The first thing I'm going to look at is the numerical part, and I'm going to find the GCF for the numerical part, 18 and 60. I'm going to start by dividing 2 out of 18 and 60, and I get 9 and 30. And then I see I can get 3, and 3 will divide into 9 and 30, and I'm left with 3 and 10. 3 and 10 have no more common factors, so the GCF part for the numerical is going to be 6. 2 times 3, that left side multiplied together. Then I look at the variable part, and I look with the variable with the lowest exponent, which is just that x. So I end up having 6x as the greatest common factor, or the GCF. Now that's the GCF, but I have to factor this, which means I have to take the GCF and put it on the outside of an open parentheses. Then what you're going to do is take that GCF and divide it from each term. So I'm taking the 18x to the third, and I'm going to divide 6x out of it. So I'm going to be left with, and whatever you're left with needs to go inside that parentheses. 6 goes into 18 3 times, and then x to the third divided by x. Remember, you're subtracting their exponents, and that bottom exponent is 1, so you end up with x squared. And then you have 60 divided by 6 is going to be 10, and those x's there will simply cancel out. So this is factored. You've pulled out the greatest common factor, and what's left is going to be the parentheses 3x squared plus 10. So if you were to re-multiply this, you should get what you started with, which is that 18x to the third plus 60x. You could always double check to see if you factored it correctly by re-multiplying to see if you get what you started with. The greatest common factor, or factoring out the greatest common factor, your answer would look like this. You're not just simply writing what the GCF is. You're going to see the GCF on the outside of parentheses, and inside you're going to have what's left after you divide it out of each term. This next one, I want you to notice that it's 3 terms. And we did find the greatest common factor for this when we were doing the example. So remember, the greatest common factor was 5x to the fourth. I'm going to write that on the outside of an open parentheses, and then I'm going to take each term and I'm going to divide out the greatest common factor. I want you to notice here, I did it in gray because ideally you want to be able to do this part in your head. So you want to be able to take 10x to the fifth and divide 5x to the fourth out, and whatever's left is going to go inside the parentheses. So you're left with 2x. And then you go 15x to the ninth divided by 5x to the fourth. You should get plus 3x to the fifth. Don't forget to bring the appropriate sign with it. It's plus 3x to the fifth. And then lastly, you divide the last term, and notice here, x to the fourth over x to the fourth will cancel out. So you're left with minus 5. Once you've factored out the greatest common factor, one term inside should just be a constant. If you have variable with each term, then you did not factor out the greatest common factor of the variables. This example that I'm doing for greatest common factor, notice here that I don't have a variable with each term. So you're not always going to have a variable in the greatest common factor. So we're asked to factor out the greatest common factor, and in this case, all I have for the greatest common factor is 4. 4 divides into itself, it divides into 12, and it divides into 20. So 4 would be my greatest common factor. There's no variable part for this GCF because 20 doesn't have a variable with it. So I won't have a variable part. I'm going to write the GCF with an open parentheses, and I'm going to divide out each term by that 4. 4x squared divided by 4 is going to be left with just x squared. Minus 12x divided by 4 is going to leave me with minus 3x. And then I'm going to divide the 20 by 4, and I'm left with plus 5. Factor out the GCF make sure you have the GCF on the outside of parentheses, and whatever is left after you divide it out of each term goes inside the parentheses. You can always double check your answer by re-multiplying the number on the outside to everything inside. Pause and try. So your greatest common factor here is 4x. It's not 8 because 8 doesn't divide into 12. So it's 4x, and then when you divide it out of each term, you should get 2x minus 3. Pause and try. So in this case, it's just 2 because there is no b with the 6. So it's just a number as the greatest common factor. And 2 divides into 4 and 6. And then you're going to divide each term by 2, and you're going to get 2b squared minus b. Don't put the coefficient of 1 here. Minus 3. Notice this next example. We're looking to factor out the greatest common factor. So it looks here that we would be doing a distributive property and combining like terms and all that. But we're not doing that because the directions state to factor out the greatest common factor. So notice that we have binomials which with each term. I have binomial. And the binomial is the same. And because the binomial is the same, we can actually factor that out. That is the greatest common factor. When we have common binomials with terms, we can call that a greatest common factor. So remember, the greatest common factor you need to write on the outside of an open parentheses. So notice here I have that parentheses x minus 5, and you need to leave it in parentheses. It's a binomial that's a greatest common factor. So to represent that binomial, you keep the parentheses there. And then you're going to take and divide each term by that greatest common factor, which happens to be a binomial. So when you divide 2 and then parentheses x minus 5 by parentheses x minus 5, well, the x minus 5 part will just cancel out, and you're left with the 2. So that's what's going to go inside that open parentheses. And then the next part, you have 3x times x minus 5 divided by x minus 5. Well, the x minus 5 will cancel out, and you'll be left with the plus 3x and close the parentheses. In this case, the greatest common factor is a binomial, and when you factor it out, you're going to be left with a binomial times a binomial. You have to be careful. Greatest common factors might not just be monomials. You might have a binomial as a greatest common factor. Pause and try. Greatest common factors is that parentheses y plus 4, and then you're going to divide it out of each term. You're left with y squared plus 6. Special factoring, the difference of two squares. When we're working with the difference of two squares, here is the rule. When we have a perfect square minus a perfect square, to factor it, it will factor into two binomials, where one of the binomials has a minus and the other binomial has a plus. In order to factor the difference of two squares, you need to know what perfect squares are. Looking at the list of perfect squares here, I have 1, 4, 9, 16, 25, 36, 49, and so on. And where this list came from, it's numerically. And to find a perfect square, you're multiplying the number to itself. So if I did 1 times 1, or 1 squared, that would equal 1. 2 times 2, or 2 squared, that would equal 4. 3 times 3, or 3 squared, would equal 9. 4 times 4, or 4 squared, would equal 16. I want you to understand where these perfect squares are coming from, and I just did the list numerically. Perfect squares are important. When we want to factor the difference of two squares, we want to understand if we have the difference of two squares. The word difference means subtraction. If in the first position is a perfect square and I have minus and the second position is a perfect square, then I have the difference of two squares and it will factor into two binomials where one will have a minus and one will have a plus. See this example here where I have x squared minus 121. I want to check, is it the difference of two squares? It does meet the condition that I have a minus sign between two terms. It could be, I check the first term and I say, well, x squared is a perfect square. It's a perfect square of x. X times x would give me x squared. The first position is a square. And then I look at the second position, which is 121, and I see it does fall in the list of perfect squares. 121 is a perfect square, and I can factor this. Factor this, you're going to take the first term and square root it. Square root, or the root of x squared, is x. Square root it, and that root goes into the binomial in the first position. And then I take the second term and I get the square root of it. And the square root of 121 is 11. And then I would put that root into the second position in the binomial. Factor the difference of two squares. It will factor into a plus minus or a minus plus. Order doesn't matter. And then the roots would go inside the binomial. That's how you factor the difference of two squares. Pause and try. So in this case, x squared is a perfect square. 81 is a perfect square. So I factor it. It's going to be x minus 9, x plus 9. Or you could have x plus 9, x minus 9. The order in which you write the binomials, it doesn't matter. Pause and try. One, you have to think a little bit because in the first position I have a number with the x squared and that number is a perfect square also. I have to make sure that I square root the whole position. So you're square rooting 25, which is going to be 5, and you're square rooting the x squared, which would be x. So 5x would go into the first position of each binomial. And then you're going to square root 16, and the square root of 16 is 4. Now this next example looks like it might be the difference of two squares. You're looking and you're saying 3x squared minus 48. 3 is not a perfect square, and 48 is not a perfect square. So you need to see, can I factor out a GCF in order to factor this? So you see that 3 is a GCF. 3 is the greatest common factor of 3 and 48. So I'm going to first factor out the GCF of 3. Once you factor out the GCF, in the binomial that's left is the difference of two squares. Now you can factor further by factoring the difference of two squares. You're going to end up with 3 times the x plus 4 times the x minus 4. When you have something that might look like the difference of two squares, but the two terms aren't perfect squares, you might need to factor out the greatest common factor first, and then factor the difference of two squares. But it's very important that if you have a GCF, that in your final answer, that you put the GCF in the factored form. Don't lose the GCF. Pause and try. In this case, the GCF is 12, and make sure it is the highest common factor, because if you don't factor out the greatest common factor, then it won't be in simplest form. And then you see you have the difference of two squares, and you're going to factor that. Make sure that the GCF is in the answer also. Pause and try. In this case, the GCF is 2. Then you have the difference of two squares. The 36 has a root of 6.